Just like look over here instead of yeah. Okay, so you're good to go?
Yeah.
Okay. No, I get it.
Can you hear? Yes. Yes. Very little. That too if I place it.
Okay, so if you overflow,
So I'm going to assume that Alright, let's start. So today we'll continue what we were doing last time, which is basically reductions between problems. So we'll start with a quick recap. Before that, just a quick announcement, the homework 2 is out, so hopefully all of you saw it. And if you have questions about it, just let me or DS know. Alright. So last week we did something very interesting and very fundamental, which is NP completeness. Okay, and we were looking at essentially, we started off with this question of are there limits to how efficiently you can solve problems, and from there we defined this notion of reductions between problems and so on. And in the process we came across interesting notions like PNP, co-NP and so on. Okay, so we also encountered this problem called Boolean satisfiability. Okay, so we'll recap that today, but just want to say we did that last time. And this notion of reductions is what we'll look at in more detail today. Okay, so we'll actually see how you can reduce between problems that seemingly have nothing to do with each other. Okay, so that's the goal for today. So let me start with a quick recap. Okay, so first we defined P and NP last time. So P, we said, is the class of all problems that you can actually solve efficiently. Okay, so problems that have polynomial time algorithms, and throughout this course efficiency usually means polytime. So this is what we said. And NP is the set of all problems in which you can verify the solution. Okay, so suppose somebody gives you a solution, you can verify it in polytime. And we said that NP is much more powerful, so because we just have to be able to verify a solution. And we also saw that most problems we'll see will be decision problems. Okay, so these are problems in which you have an instance and you want to answer some yes/no question about it. Okay, so So we said we are looking mainly at decision problems, and here the answer to everything is like yes or no. Okay, so that's why you can think of a problem as simply the set of all yes instances. Okay, so this was a nice way of looking at things. So every instance has some size, and it's just a yes or a no instance. And we said one example of a decision problem is one thing could be you are given some Boolean formula and you could ask, is this formula satisfiable? Okay, so that's an example of a decision problem. And you could also have natural optimization problems like maximizing the independent set. Here a decision version of this would be, is there an independent set of size at least k? Okay, so that's a decision version of the same maximization problem. And so let me also recall this notion of reduction. So we said that we introduced this notation of less than sub p, and basically it means problem A can be reduced to problem B with polytime reductions. Okay, so that's what this means. And so intuitively it's like saying problem A is easier than problem B, okay, or it's not much harder than problem B. And formally what we said is if you have any instance I of problem A, having a reduction implies that you can solve that instance. So the time taken to solve that instance is at most some polynomial in the time taken to solve a similar sized instance for B. Okay. So it's a poly I times time B of, you could have a polynomial slowdown. Okay, and we said that polynomial factors are all okay for us when we are dealing with reductions. Okay. And so this is what we mean by reductions. And we saw two examples. Okay, so we said that there are two natural notions of reductions, and the first was this Cook or Turing reductions. Okay, so here, if you all remember, so basically what we said was you want to show that problem A is easier than problem B. Okay, so you say that suppose I have an oracle for solving B, then I can come up with an efficient procedure to solve A. Okay, so this is what we call Cook or Turing reductions. And here it's a notion of, suppose you had a black box which we call an oracle for solving B, then you also show how to solve A. Okay? And the difference between CARP and Turing reductions were basically that you could make multiple calls to this oracle. Okay? So in a Turing reduction, while in a CARP reduction you actually transform one instance of A to another instance of B such that the answers for the two are exactly the same. And so we illustrated the difference between these two by saying, suppose you want to reduce from the problem of satisfiability to the problem of unsatisfiability, which means you are given some formula and you want to show that it is not satisfiable. So for that we said that there is no known efficient way of certifying this. Okay, so of certifying that a problem is unsatisfiable. While if you just look at Turing reductions, it's trivial to reduce between sat and unsat, because you just do something and then you negate the answer. So if you had an oracle for sat, you could use it to solve unsat, and vice versa. Okay, so this was just a quick recap, and we also defined what NP hard and NP complete are. Okay. So, we said that a problem Q is NP hard if satisfiability reduces to Q. So that's when we said the problem is NP hard, and we said it's NP complete if the reduction works both ways. So Q is NP complete if and we said that usually when we say reduction, we mean CARP reduction. Okay. So this is the standard notion in complexity theory. When we say reduction, we mean a CARP reduction. So we want to transform every instance. Okay, so last time we also saw a very simple example. So I'm going to go to that in a bit. But first, this is a picture of how you should think of NP hardness, NP completeness. Okay, so you have this class NP, which is this oval-shaped thing, and then NP contains P, and hopefully it contains, presumably it contains things that are outside P. We don't know, but we believe so. And of course, there are these NP-complete problems. We'll see a bunch of examples. So satisfiability is one of them. Max clique or max independent set is one of them, and so on. And there are problems that are harder. Okay, so there are problems that are much harder than NP-complete, and they are all, of course, NP-hard. Okay, because there is a reduction in one direction, but they don't reduce to SAT. Okay, so those are the NP-hard ones. Okay, and P is poly times orthogonal as well. Okay, so let's, and we also started off last time with describing this chain of reductions, right? So we said that we're going to move from satisfiability, and we're going to show that this is polytime reducible to what we call 3-SAT. So I'll just recap these in a bit, but this is what we said. Then this you can reduce to problem of independent set. So this is a graph problem. Okay, so we'll see this reduction today. And this reduces to vertex cover, which is also a graph problem. And yeah, and this basically reduces to subset sum, and this reduces to this machine scalability. So this is a picture I drew towards the end. So I just want to, some sense, just go through these reductions today. Okay? So the goal of this picture is to tell you that, these are problems that seemingly come from different domains. Okay? So some are some graph problems, some are some numeric problems. So subset sum is a numeric problem. So we'll define that in a bit. And the point is that from the point of view of difficulty, they are all in this equivalence class of what are called NP-complete problems. Okay? So that's the goal. So any questions so far about definitions of NP-completeness and so forth? Yeah?
If they're all in the same equivalence class and NP-complete, couldn't you then say that the chain goes the other way too?
Yes. So often the easiest way of showing this is not to show each pair, but you show this whole thing and then you show this reduces to this. Okay. So it's often very easy to write problems as SAT. Okay. So many problems that you can think of where you can verify the solution easily, you can write it as SAT. Okay. So you'll see some examples of this in your homework. So those will be the easy parts of the homeworks. So yeah, very often going back and forth is tricky, as you'll see. Okay, so any other? With something we did last time. Okay, so what we saw last time was we saw a reduction. Not in full detail, but we saw the outline of a reduction from SAT to what is called 3-SAT. Okay. And we introduced this notion of a CNF. Okay. This is one way of writing Boolean formulas. Okay. So it's called a conjunctive normal form. So basically, it's one standardized. Normal forms usually mean it's some standard way of writing something. Okay. So any Boolean formula, you can write it as a CNF. And we said that phi is, you have a bunch of ORs, okay, so it could be like x1 bar, x2 or x3 bar, something like this. Bar is just the negation. And you have an AND of these things. Okay, so you might have x2 and x1, x2. So, okay. So you have a bunch of what we call clauses, and you have an AND of them. And each clause is an OR of a bunch of what we call literals. Okay. So this whole thing is a clause, and this is a literal. So these are words that you might want to remember. Okay, so literal just means some variable or its negation. Okay, so x3 bar is a literal. So they come up in reductions. And 3CNF formula is something that's very similar, except that it has exactly three literals in every clause. So same as above. Three literals. Okay. And the last time we saw how you can start off with some CNF formula and reduce it to a 3CNF, okay, of size which is not much bigger. So, do you guys remember how we did it? Yes. So the idea was basically to introduce new variables and kind of split, if a clause is too big, we are splitting it into roughly 2 equal sized pieces by introducing one extra variable. And this process, you'll cut down the number of literals in every clause, and the formula size doesn't grow by too much. Okay, so this is the idea we saw last time. But so from now on, when we reduce to different problems, instead of reducing from SAT, you can reduce from 3 SAT. Okay? So because we showed that SAT reduces to 3 SAT. Okay? So this is a nice thing. So somebody could have proved an NP hardness reduction, and then you can use that. So you can use the final problem as a starting point for your reduction. Okay? So this is why this equivalence is very nice. Okay, so let's see the first kind of non-trivial example of a reduction. Okay. And this is from 3 SAT to this problem called independent set. Okay. So how many have heard of this problem of independent set? Just to get a sense. I guess only a few. So let me define this. This is a graph problem. So you are given a graph. The graph is usually given with a set of vertices and some edges, right? So you have a bunch of nodes, and you have some edges between them. It may not be planar. So every line I drew is an edge, and every point is a vertex. Okay, so this is a graph. So we'll see more on graphs starting next class, but it's just a basic problem. And the goal is pick the largest set of vertices S. Okay, so V consists of all of these. All these vertices. Now of these you want to pick the largest possible set S, it is a set of the largest size, such that no two elements of S have an edge between them. Okay. So this is what's called the independent set problem. So for instance, I can't pick these two vertices, okay, so the ones that I circled. So they cannot be part of S because they have an edge between them. Okay. So the goal is to pick as many edges, as many vertices as you can, such that there's no edge between them. So these sort of problems come up when you have some conflicts. Okay, so let's say you have a bunch of courses, courses are your points, and you put an edge between them if they have a conflict. Okay. So then, in some sense, you want to pick a collection of things that don't have any conflicts between them. So this is the kind of situations where which people model using independent set. And so this is a natural problem, it turns out. And you want to find independent sets that are as large as possible. Okay, so typical. But this is not a decision problem. So how would you make it a decision problem?
Is there a set which is there a set possible which is in that?
Well, that is always true, right? Because you take one vertex, it's always an independent set.
Don't pick vertices with the maximum number of edges.
Sorry?
Don't pick vertices with the maximum number of edges. Like we can have a greedy algorithm that sort of goes.
No, but I'm not asking for an algorithm. I'm just asking for give a decision version of this problem. Okay? So this, as I see it, is a maximization problem.
Can there be more than this set of vertices naturally?
Yeah, that's one thing.
Resonance are always last K.
Yeah, so this is the same thing both of you said. So basically, given a k, is there an independent set of size at least k? So, question. Given k, of size k. Okay. You could also ask size at least k, but it doesn't matter. Okay. So this is a natural decision version, and we want to say that this problem is NP complete. Okay. So to prove NP complete, you have to prove both directions, right? So you have to prove that firstly, this problem reduces to SAT, and also 3SAT reduces to this problem. Okay. So in this case, this problem reducing to SAT is very easy, so I'll leave that as an exercise. Okay, but it's, exercise is in, you can just think about it and you'll come up with it in a few minutes. Okay, so basically, what you should think of is, suppose there is a set of size k. Can somebody convince you that there is one? That's very easy, right? You just exhibit it. Okay, so that's how you prove that it's in NP. Okay, so let's now see why 3SAT reduces to independent set. Okay. So what is the goal here? Right? So how do we prove that 3SAT reduces to independent set? So to prove any reduction, what you've got to do is start with some instance of this first problem, and you've got to construct an instance of the second problem, which is not too much bigger. And this should be a yes instance if and only if the original instance was a yes instance. Okay? So that's what we have to prove. Right? So the goal is start with some instance of 3SAT. Okay? An instance of 3SAT is just a Boolean formula, right? It's just a formula where you have 3 literals per clause. So it's phi, which has some first clause and the second clause and so on. Then you have some m clauses, let's say, and you have n variables x1 through xn, and each one is, you have 3 literals, maybe x1 or x2 or x3, x3 bar, something like this. So I just drew a 3SAT formula for those who can't see. Okay, and from this you want to come up with a graph G such that this graph has an independent set of size at least k, of size k, if and only if this formula is satisfied. Okay, so it seems mysterious, right? So how do you construct a graph such, and you have to figure out some k, okay, such that this graph has an independent set of size k, if and only if this formula is satisfied. Okay. So let's see how you do it. Okay, so this is a somewhat tricky thing. So I'm going to slowly lead towards this solution. Okay, so graph G, and so you want to go from P to graph G. Okay, such that G has Okay. So is the goal clear? So this is exactly what we mean by card production. Okay. So you start with an instance of one problem, you come up with an instance of the other, such that this is yes if and only if this is yes. Okay. So this is the definition of a reduction. Okay. So any questions on this?
Can you repeat that, please?
Which one?
Can you repeat that, please?
Yeah, so I'm just saying that proving that 3-SAT reduces to independent sets is equivalent to this. Okay, so given some formula phi, which is an instance of 3-SAT, you want to come up with a graph G and this parameter K such that G has an independent set of size K if and only if this formula phi is satisfied. Okay, so this is what we mean by reduction. So this shows that if you can solve independent set efficiently, you can solve 3-SAT efficiently. And so you should. And since we believe 3-SAT cannot be solved efficiently, this is kind of indication that independent set cannot be solved efficiently. Okay? So that's the context for this. Okay. So how do we go from a formula to a graph? So a formula has bunch of variables, bunch of clauses, right? So okay, so let's start with it on the left. So maybe its first clause is x1 or x2 bar or x3, and something like this, right? And note the goal, right? So we want to show that this formula is satisfiable if and only if this graph you construct has a big independence. Okay, and what do we mean by a formula being satisfiable?
There's one set of input.
Yeah, so there are some values for xi's, true or false, such that each of these clauses becomes true. Right? So that's what we mean by satisfiability. But one thing to note is that in some sense x1 you have to set it, so you have to so if you think about it for a little bit, the way you can prove this sort of a thing is to say, I construct this new graph G. Okay. I don't know how I'm going to construct it, but let's say I can construct it. But I should be able to say that if G has an independent set of a certain size, then I should come up with a satisfying assignment for this phi. Okay. So that should be the goal. Okay. So I'm given some phi. I want to come up with a graph such that a big enough independent set in this graph should allow you to recover a satisfying assignment. So that is how you usually think of when this is how you try to build a reduction. Okay. So let's try to see how you do that. So a natural way is, you could think that okay, maybe I have literals for maybe I have some x1 and I have x1 bar. I have a vertex for each literal. Okay, so x1 bar, and maybe I connect them by some edges, and you could have stuff like this, x2 bar, and okay, so this is fine. So if any independent set will try to pick only one of them, so in some sense this is an assignment. Okay. But you'll quickly see that how do I incorporate clauses into this? Right, so there's no easy way of incorporating clauses into this, right? Because a clause is like one of these things at least should be satisfied. Okay, so maybe you might think, okay, so maybe I have variables for every clause, okay, and try to say that maybe I know that in a satisfying assignment at least one of them is true. Okay, so maybe I can try to capture that. Okay, so this doesn't really work. So let's start again. So let's start having things for clauses. So this clause is x1 or x2 bar or x3. So maybe I'll have x1, x2 bar, x3. Okay. And you have a different clause which is x2, x1 bar or x4. You have a different clause here and so on. Okay, so this is for the first clause, for the second clause and so on. So now what I want to do is, I know that if the formula is satisfiable, I should be able to pick at least one thing per clause, right? So maybe I can pick two variables per clause, but 2 or 3 is also fine, but there should be at least one, right? Only then the formula is satisfiable. So let's say I have m clauses and I tell you, okay, find me an independent set of size m in this graph. Okay, so far I haven't put any edges. So this is trivial, right? There's no edges, so you can basically pick any m vertices, it will be an independent set. Okay, so I have to do better than this. So firstly I should prevent conflicts. Okay, so I should prevent any x1 from being picked if any other x1 bar is picked. So do you guys agree? Yes. So because if there is x1 somewhere and x1 bar somewhere else, okay, I shouldn't allow both of these to be picked. Okay. So I can throw in an edge between these two. Okay. So in any independent set, I won't be allowed to pick both of these. Okay. So I can do the same for any x2 bars that exist. Maybe there's an x3 bar somewhere at multiple places, and I put edges between all x3s and all x3 bars, all x1s, all x2 bars, and so on. Okay. So this suddenly looks much better, right? So now, if I find an independent set of size m, and it so happens that there is exactly one from each of these groups, then I claim that I'm done. So why is that? So what I want to claim is, suppose in this graph there is I find you an independent set where there is exactly one vertex from each of these groups. Okay, so a group corresponds to a clause. Then I claim that I have found a satisfying assignment. So everybody see why, or does anyone see why?
You said all those reference to I and it will satisfy.
Yeah, so basically the fact that it's an independent set means that you could never have picked a variable and its complement. Okay? So if you ended up picking this and something else over here, then it means that picking x1 bar to be true, x2 bar to be true, which is like saying x1 false, x2 false, and let's say this is some x5, right? So an x5 to be true, you've made all the clauses satisfied. Okay. Basically, you have at least one satisfying thing in each clause, and basically you avoid contradictions by putting edges between x1 and x1 bar. Okay. So
you need to make sure only one is picked.
yeah, exactly.
All of them together.
Right. So what we want to do is, so what he's saying is, right now I assume that I have this independent set where you have exactly one vertex picked from each of these clause groups, right? And what's the easy way to ensure that? So you just want, you don't want two guys from this block to be picked. An easy way is to just put a triangle between them, right? So if you add these edges, okay, then there's no way I can pick more than one from this clause. Okay. So it's actually very easy. So you just add a triangle between each of these clauses, and that's it. Okay. So you add these triangles, and you have these edges that go across. And now if you find an independent set of size m, okay, so if you find an independent set of size m, so the claim is any independent set corresponds to assignment for phi. And this is actually, we just proved it. Okay, so we basically said if you have an independent set of size m, then there's no way you could have, there are m such groups, there's no way you could have picked more than one vertex in each group, so you should have picked exactly one in each group. And you could not have picked any two that contradict each other. Okay, so you could not have picked, yeah.
Can you repeat why we need the triangles?
Yeah, so what we said before is, suppose you didn't have the triangles, and I asked you to find an independent set of size m, then you could ignore a few of these clauses and maybe pick two vertices. It could be possible that you pick two vertices in one thing, two vertices in another, and maybe nothing from this. And that would still be an independent set of size m. But it would not lead to a satisfying assignment for phi because one of the clauses is not satisfying. Okay? So in some sense we need to enforce every clause to have at least one thing picked. Okay? So that's why we need it.
Yeah.
Yeah.
But what if we pick, for example, x1 was false, by the whole clause? Like one of the independent sets has a number of x1 or something. Because,
Can you share again?
yes, the clause, the first one, the first one,
Yeah.
not all of them will make this like the
Yes.
viable.
Not all of them will make sense.
Yeah.
Yeah.
What makes sure like the one you pick from N will satisfy that one, for example?
Right. So what I'm saying is,
Yeah.
if you can find an independent set of size m, okay, then firstly you agree that there has to be exactly one from each clause. Right? So let's say I picked. So you're saying maybe I picked x1 from the first one.
Yeah.
So okay, maybe I picked x1 from the first one. But now in the second one I could not have picked x1 bar because there's an edge between x1 and x1 bar. So okay, so which means I must have picked something else. And so on, right? So now the point is, this will lead to another satisfying assignment, but it will always lead to a satisfying assignment if you could find an independent set of size m. So yeah. So if there are multiple satisfying assignments, you will have multiple independent sets. So good. So any other questions? Okay. So what you said here is. Any independent set of size m corresponds to a satisfying assignment. Note that this is only half the proof. Okay, so this is actually the non-trivial half, but you also have to verify that if there is a satisfying assignment, for phi, then there exists an independent set of size m. So this is the easy part. Why is this true? Yeah, so this is very easy to check. You just look at the assignment. From the assignment, you can now look at this graph. And let's say the assignment was x1 equals true, x2 equals true, x3 equals false, or something like this. I'll just pick out one thing from each clause. And I know I can always do that. And clearly you will not encounter any contradictions because only one of x1 and x1 bar is picked. So this part is easy. Okay, so this is common in reductions, where one of the sides of this if and only if will be easy to prove, and one side will be the tricky part. Okay, so often the part where you go from this problem back to SAT will be the tricky part. So you'll have to deduce an assignment from some independent set somewhere. Okay. All right. So this is a reduction from 3SAT to independent set. Okay. So now we'll see this other problem. Okay. So this will be an easy reduction. So remember, I want to just do this chain to give you a sense of various kinds of problems. Okay, so this will be the easy part of the chain. So I'll go from independent set. I'll show that it's easier than this problem called vertex cover. Okay, so what is vertex cover? So this is again a graph problem. Okay, so you have our favorite graph. And this time, this is a minimization problem. Okay, so vertex cover problem is given G. Pick a set of the smallest possible size that covers all the edges. Okay, so what do I mean by covers? It means that each edge has at least one endpoint in S. So this is what I mean by covering all the edges. So I want to pick a set S. Okay, so I want to pick again a set S of vertices. This time the goal is for every edge, at least one of its endpoints must be picked. Okay. So this is, sometimes people call this some kind of a policeman type problem. Okay, so these are all roads and these are intersections. You want to place as few policemen as possible such that the policeman can see all the roads. Okay, so they want to be able to look into every road. Okay, so this is one way people call this. Okay, so for example, in this small example, maybe
The middle one?
yeah. So yeah, you could also pick the middle one, but let's say I pick this one. Okay, so then this edge is covered, this edge is covered, this edge is covered, right? And these guys are not. Okay, so maybe I pick this one also. Okay, so then this, and this are covered.
One.
And then there's these two left, right? These two left. So maybe I pick this, and this will end up covering these two also. So this is a vertex cover of size 3. Okay, so I have 3 vertices that I pick. And the goal is to pick as few vertices as possible so that you cover all the edges. So, questions about the definition? And again, you can make this a decision problem. Decision problem, you can always say the same thing. You say, is there a vertex cover of size at most k, okay, or size equal to k, for simplicity. Okay, so I want to claim that this problem is very related to independent set. So maybe some of you have seen the connection. How many of you have seen the connection between this and independent set? Oh, good. Okay, so then you can try to think about this. Okay, so I claim that this problem is very closely tied to independent set. Okay, so independent set was this problem of bunch of vertices with no edges between them, right? And here, in some sense, it's like you want to pick vertices that cover every edge, right? So suppose you take a vertex cover and you look at the vertices that are not in the cover. So what can you say about those vertices? Yeah, so the point is, suppose, I mean this is a vertex cover, right? So we've just established that this is a vertex cover. If you look at vertices not in the cover, can they have an edge between them? So if they had an edge, then this would not be a valid vertex cover, right? Because a vertex cover has to have one endpoint of every edge. Okay? So vertices not in the cover cannot have any edges between them, which means they have to form an independent set. Okay? So this is the connection between them. So for any, so this is a lemma, or you can say observation. where is a vertex cover. Then V minus S is an independent set. Okay. Note that the converse is also true, right? So if you have some set S such that V minus S is an independent set, then S has to be a vertex cover. Okay, because all the edges in the graph must be only between, must have at least one endpoint in S. So this is an easy if and only if statement. So, and this gives a reduction between from independent set to vertex cover. Okay, so I want to claim that So how is this? So here again, so what do we want to show for a reduction? Right? You start with the problem instance of independent set. Instance of independent set has a graph G and a number K. And your question is there an independent set of size K? I want to now come up with a new of an instance of vertex cover, which is again a graph and some other integer. Okay, so K prime. So how would you come up with such a thing?
It's n minus k. So number
The same graph and with n minus k. Okay, so I claim, yeah, so this is k where n is number of words. So everybody see this? So basically, if you ask to find a vertex cover of size n minus k, then it's exactly the same as asking one to find an independent set of size k. Because of this observation. Okay, so because if S is a vertex cover, then V minus S is an independent set and vice versa. So, and that's why it makes sense that one is a maximization problem, one is a minimization. Okay, so it's n minus that. So this is an example of easy reduction. So what we've seen so far is basically going from SAT, which is seems like a problem from logic, to a problem on graph, right? So to a couple of problems on graphs so far. Okay. So the next example we'll see will have numeric things. But maybe I'll pause for a minute and maybe take questions. Do you guys have any questions about this or the previous round? Okay, so good. So then we can probably continue if there's no question. So I now want to talk about this other problem called subset sum. Okay, so this is something which you've kind of seen before, and the problem is the following. Okay, so given a bunch of numbers, given numbers A1, A2 up to AN, okay. So I give you a bunch of numbers A1 through AM and I give you some S. This is the target sum. And the question is, do there exist a subset of these numbers that add up to S? Okay. So, how many of you think this problem is easy? I mean, this problem can be solved. You've all done dynamic programming, you've all done stuff. So, So I give you a bunch of numbers and I tell you do a subset of these add up to S. So this is very much something like this coin change type problem, right? Because I have this sum S and I want you to figure out if some of these things add up to S. So can you do this? I mean, what's the natural dynamic program to do this? Maybe this is actually on the homework, but yeah, you can think so.
Sum minus the whatever sum we have been given, we subtract with the element which we iterate through our in the set.
Yeah, but so I'm saying, give me a simple dynamic programming way to solve this.
Greedy.
Sorry?
It's not.
Well, greedy doesn't quite work, right? So you will say that maybe S is not expressible as in terms of the greedy thing.
Start with A1.
Mm-hmm.
A1 is in, then recurs on A2 to AM and S minus A1.
Okay.
Or else recurs on A2 to AM and S.
Yeah, so this is
And
a
you take the
this is a recursive way of solving it, and the way to make it, the way to turn it into a dynamic program is to have an array which stores if array of size S. Okay, so array of size S. And this tells you if array of sizes, maybe you also have, as you said, you keep track of this subset that you are interested in. Okay? And this tells you if S can be, if a certain value can be represented using only some subset of these numbers. Okay? So you could have, essentially you could have an S times M array. So this is the amount of space. Okay, and using this you can find if, this is also the time. Using this you can find out if this is possible or not. Okay. So why am I saying this is NP hard? So this seems reasonable, right? So this is a correct algorithm, and this seems to find if if you have a subset of them adding up to S or not.
Is it because S is unbounded? That S could be very, very large.
You're close. So basically, the thing to think about, which is, so I gave this example because you should get used to thinking about what the problem size is. Okay? So what is the problem size here? Right? So I have to give you a bunch of numbers A1 through AM, and I have to give you S. So suppose I just write S in decimal or binary or some usual basis. Okay. So what's the number of bits you need to represent S?
On base 2.
Yeah, log base whatever you are using of S. Right? So if you represent things in binary, you would take basically log base 2 of S many bits to write down S. Okay. The same is true for the AIs, right? So you will just use log base 2 of the A1 plus log base 2. Okay. So this is the total input size. And technically speaking, when we talk about polynomial time algorithms, we care about algorithms that take time which is polynomial in the input size. Okay? And here the input size is only something like log S plus a bunch of these things. Okay? So it turns out that we don't know of any algorithm that takes time polynomial in log of S. Okay? So finding such an algorithm is actually NP hard. Okay? So this is a slightly subtle thing that you have to that shows up in these kind of problems. Okay, so the same is true in factoring. Okay. So factoring is one of these problems that we don't know how to solve in polynomial time. So if you are given a number n, break it up into P and Q such that n equals P times Q. So P and Q are both bigger than 1. So this is a factoring problem. Now you can always do this in square root n time, right? Because you can check all factors. I mean all possible factors. But this is not a polytime algorithm because in some sense the size of the instance is only log n. Okay? So this is actually exponential in log n. Okay? So it's the same kind of thing that's happening here. Okay? So you want so this is often something you have to keep in mind when you think of algorithms with numbers in them. Okay? So the input size is just it's the amount of space you need to write down these numbers, okay, which could be significantly smaller than the numbers themselves. Okay. So now I want to claim that this is actually NP hard. Okay. So in some sense you don't expect to find an algorithm which is polynomial only in this. Okay. So but meanwhile, is this notion clear? This thing of so this is why this is not a contradiction that. The fact that there exists an O of S times M algorithm is not a big problem. It's not a contradiction. So let's prove this in a bit. Okay, so again, to prove this, what you have to do is you have to start with instance of vertex cover to come up with an instance of subset sum. Right? So note that these are seemingly very different looking problems. Right? So one is you have a graph G and you have some K. Question here is there a vertex cover of size K? And what you want to come up with are numbers A1 through AM and some S. You want to say is there a subset of these guys? There's no K on the right side problem. Okay, so the subset has no size limitation or anything, and you want to find if there exists some subset that adds up to K, that adds up to S. So let's simplify this. Okay, so let's start with an easier version of this subset sum. So let's try to reduce from vertex cover to what I call vector subset sum. Okay. So instead of these AIs being numbers and S being numbers, so let's think of vectors. Okay, so maybe I ask you to come up with A1 bar, A2 bar, these are all vectors. AM bar. The goal is, does there exist a subset of these vectors that add up to some target vector S bar? So this problem turns out is more like subset sum. Is more like vertex cover. So what I want to illustrate here is sometimes when you want to reduce from one problem to the other, you might want to come up with an intermediate problem, okay, and reduce vertex cover to this vector subset sum, and then reduce to subset sum. So this is something that you should keep in mind when you're doing reduction. Okay, so sometimes it's just hard to come up with the final thing. Okay, so it's easier to slowly transform this problem into the kind of thing you want. Okay, so let's first see this vector subset sum. So any questions? So let's. Okay. So you want to pick a few edges, a few vertices, so that you cover all the edges, right? So this sort of a thing, you naturally want to think of some kind of a bipartite graph, right? So any covering problem, turns out you can say, oh, okay, so I have vertices on the left, and you have these edges on the right. So remember, I have this graph. So for every edge, I can put a vertex on this side. Okay, so in this case, there are 7 edges. So, okay, so maybe it's one. Okay. And vertices, let's say I label them as A. Okay. So I have vertices here. And you can say that if I pick vertex A, then I'm going to cover edges 1 and 4, right? Because this is what we were doing. So we can try to say, okay, so this is connected to 1 and 4. Okay. So the reason I do, so this is a standard way of thinking about covering problems. Okay, so you want to pick a few things that cover, some other kind of objects that you want to cover. Okay, so in this case, you want to cover all the edges using the vertices. Right? So you put the vertices on the left, the things that you want to cover on the right. Okay, so this is a usual. This is how you also think of this problem called set cover. Okay, so it's a nice mental way to think about this. And B that way covers 1 and 2. So B is incident to 1 and 2. And in this language, so how can you phrase this problem of vertex cover? So I have edges on the right, vertices on the left, right? So and each vertex covers a bunch of edges. I want to say that, for a vertex cover you have this guarantee that every edge has at least one vertex incident to it, right? So how can you formulate vertex cover? So I have K and I want to see if there's a vertex cover of size K. So
Asking how to represent it like this.
yes. So in this language, how would you phrase it?
So there would be a subset of the vertices of size K that such that there's a line bound to every edge.
Yeah. So for every edge, so for every vertex on the right, okay. So you want to be able to have at least one of these things on the left picked, right? So you want to pick K vertices on the left, okay, such that for everything on the right, you have at least one of its neighbors picked. Okay, so this is an easy way to write vertex cover. So for every node on the right, at least one neighbor on the left is P. Okay. So this is when you would say that it's a valid vertex cover. Okay. So now I want you to think of for every vertex on the left, okay, so let's say you have a 7-dimensional vector, okay, so for this vertex, okay, for vertex A, I want you to think of a VA, okay, such that, so vertex A is connected to 1 and 4, right? So let's say I put a 1 in positions 1 and 4 and I put zeros everywhere. So this is what is called the adjacency matrix type representation for a bipartite graph. Okay. So it's basically you have VA and you have VB, which is, so B is connected to 1 and 2. So I'll put a 1 in these positions 1 and 2 and I'll put 0 there. And similarly you have VC and so on. Okay. So now how can you phrase this vertex cover problem? So I want to say, I want to pick a few vertices on the left, right? So I want to in some sense pick a few vectors. And
So let's say if you sum all of them,
Or
you have one
yeah, so I guess many of you see this, right? So basically what's going on is you want to have, for everyone on the right, you must have at least one thing on the left, right? So which is like saying, if you took a vertex cover and summed up these vectors, you must have at least one in every coordinate. Okay? So if you had 0 in a coordinate, it means that so every coordinate corresponds to some edge on the right and that one had no neighbor. Okay? And that's not a valid vertex cover. So easy observation is if S is a vertex cover, then you look at this sum over A, or let's call it X in S of V sub X. Okay, so I have a vector for every X and I'm summing this for all X in S. And this vector has every entry bigger than or equal to 1. So there's a couple of issues with this, right? So here, so actually maybe you can come up with these issues. So what are a couple of issues with this sort of a phrasing? So this is correct. I mean, what we are saying is if S is a vertex cover, then sum over X in S Vx has every entry bigger than or equal to 1. But what we actually want to come up with is a vector subset sum problem, right? So I want to say that this graph has a vertex cover of size k if some of these vectors add up to some other vector, right? But here it's not adding up exactly to this vector. And all you have is this bigger than or equal to. Okay? So this is an issue, right? So you actually want to come up with some target vector and say that these guys have to add up to this. Okay? So this is one issue. Okay. And equal to 1 versus bigger than or equal to 1. So it would be nice if you would say equal to 1. Okay. And what's the other issue? So note that the vertex cover problem also has a k in it. Okay, so you want to have a k such that, you want to know if there's a cover which has exactly k vertices, okay, or at most k vertices. And this way of formulating things, you lose track of the k, right? So there's no way you're keeping track of this k. Okay. So that's the other issue. So k is lost. That's issue 2. Okay. And so it turns out this you can actually remedy. Okay, so let's look. So we're looking at vertex covers to vector subsets now. So now what you can do is, so the k1 is easy. So what you can do is you can maintain an extra coordinate, okay, which you want always, so which keeps track of how many sets you pick. Okay, so for every set, for every VA, you have whatever you had before. So you have 1, 0, 0, 1. And you have this extra coordinate which is 1. Okay? And same thing for VB. It has this 1, 1, 0, 0, and it has the extra coordinate that's 1, and so on. Okay? So this is 1 for all these guys. So now if you want your target set to have a k in the last coordinate, okay, then it means that you are exactly picking k elements, right? Because there's no other way you could have gotten k on the right side. Okay? So if a bunch of these add up to a vector which has k on the right side, then it means that you've exactly picked k of them. Okay? So that's one nice thing. Okay, but there's still this issue of picking more than one. Okay. So how do you get rid of that? So this is again a little bit tricky. So I will mention what the answer is, and so it's one of these things where it's better for you to go back and work this out. So what I want to do is, along with these sets for every vertex, so I have these up to VF. I also want to have these UIs, which like U1, U2 up to U7, which just have precisely one entry. Okay, so it's like this is 1, all zeros, and even the last element is 0. Okay, so that's the key difference. The last element is 0. So these correspond to this. Okay. The claim is that now you can just hope for, now you can just try to make the sum all 2's and a k. Okay, and I won't go into the details of this, but basically if you have vectors like this and a bunch of them add up to all 2's and a k, then you're ending up picking, in some sense, one from each, and you are picking at most k of those vertices. Okay, so this turns out corresponds to a vertex cover. So we're going to check this. Okay, so maybe I'll leave that as a exercise.
If it's all twos, doesn't it mean that all the pages are being speculated?
Sorry?
If it's all twos, doesn't it mean that all pages are being speculated?
Yeah, so the point is you can't pick one edge by more than 2 times. Okay, so I'm using that fact implicitly. So I'm not getting into this because is that what you're?
All of the, I'm saying that all of the vertices are being picked, like n vertices are being picked for it to have.
No, because I'm allowed to use these guys. So how do I get all 2's and a k, right?
It should be all 2's and an n. All 2's are picked, it's going to be n.
That's the thing. So I also have these extra vectors that I could use. Okay, so these vectors have, so these are basically this diagonal things, right? So the first vector has, it has just 1 in the first position. I didn't write that. So it has 1 here, 0 here, and 0. Oh, okay. So this is what it is. This is the first vector, this is the second vector, and so on. So there are these extra vectors, okay, which I can use to remedy what I could not do. Okay, so basically, I could have used just these guys, right, to get an all one thing. Okay, but then that will have a 0 on the right. Okay. So the fact that I have a k on the right means that I am picking k of these guys. Okay, and I want to say that I should have picked at least one in these things to get an all 2's vector, because using a subset of these lower guys, I could not have gotten more than an all 1's in that. Okay, so that's the thing. Think about this for a bit and you'll realize that if a subset of the vectors on the left add up to all 2's and a k, then it should be that you found a vertex cover and you picked a bunch of these other guys that made it all 2's. So,
Oh, it's only a subset of those extra ones that you added, not all of them.
not all of them, because suppose I covered an edge twice, okay, then I don't want to pick that. Okay, so that's the, yeah. Yeah, so it's one of these things that if you check it, it will become much cleaner. Okay, so I won't go into the detail. So what this shows is that vertex cover reduces to this vector subset sum. How do you go from vector subset sum to regular subset sum? This is again a trick, okay, so you can think of these vectors, you can try thinking of them as binary strings, right? But binary strings don't have k's and stuff in them, so it's a little bit trickier. And also, when you add things, you get carries, okay? So you've got to pick a base that is bigger than, turns out it's bigger than 3, okay, so base 4 works. Okay, so this is, I won't go into it, but the notes I'll link to will have the full proof. Okay, but the right way to think about this is by first thinking of it as a vector version, and then you can make the vector to be numbers in a somewhat straightforward way. Okay. So here again you will see that the numbers involved are all huge, and they necessarily have to be, okay, because the numbers were small. We said that you can solve this problem in time O of s times that. Okay, so that's why these numbers are all exponential in it. So that's subset sum, and from here to parallel scaling is easy, but I don't have time, so let's not do that. So, but one thing I want to say is, I want to do these concluding things now, because next class we can start with graphs. So what this suggests is, if a problem is hard, question is, should you give up hope, right? So that is not always true. Okay, so for many problems, actually most problems that you really care about solving are NP hard. Okay, so it's an unfortunate fact of life. Okay, so the way you deal with this is usually by coming up with what are called approximation algorithms. I try to say, okay, finding the optimum is difficult, but maybe I can find something that's approximately optimal. Okay, so these are what we call approximation algorithms. And clearly this doesn't make sense for a decision problem. Okay, so it makes sense only for optimization problems. But we'll see some examples. We've already seen examples of this, like this parallel machine scheduling, shown that this local search algorithm is always at most a 2-factor away from optimal. So you can prove things like this for other problems as well. Okay, so these are called approximations. And turns out there's this whole interesting theory of sometimes some problems are really bad. You can't even find approximate solutions to them. And how you prove that something has no approximate solution is actually a very non-trivial thing. Okay, so people didn't know how to do this until about 20 years or so. Okay, so it might sound like a long time ago to you guys, but it wasn't that long ago. So yeah, let's stop here. Maybe we'll chat a little bit about these later in the course.